electrical waveforms. More information about these waveforms under electronic tutorials. This is the reference for this video. And we're going to cover typical waveforms that you're going to encounter in signals, in electrical signals. The most common one is a sine wave, square waves, pulse waves, triangle waves, and sawtooth or ramp waves. There are a set of important parameters that it's important for you to know. Normally we have two axes, and on the x-axis you represent time, and this is where you have information about your period, which the units are seconds. And there is a way to relate the period with frequency, which is the period is the inverse of frequency and vice versa, and the units used for frequency are hertz. You also have the y-axis, and this is where you have voltage information. Here you have amplitude, volts to peak. You have volts peak to peak. You have DC offset. You have duty cycle, which is a percentage, it's a ratio, and duty cycle only applies for square waves. Let's go over an example where we're going to see all these concepts applied, all these parameters applied. So here you can find a signal that is represented, can be a signal on an oscilloscope or on a piece of paper. I have my ground, my reference point in blue, and I also have how much information do I have per division. I have 500 millivolts per division on your y-axis and 500 microseconds per division on your x-axis, on your time axis. The type of wave that you have, it's a sine wave. The period is going to be 1 millisecond. So how do you find the period? You pick one point, the random point on your wave, and you trace the wave until it repeats. So the wave here is going to repeat over here. I apologize, a little bit of lag on the computer. So it's going to repeat at this point. So it starts here and it goes up to there. So notice that you have two divisions between these 2 points. So 2 times 500 microseconds. The frequency is going to be the inverse of the period, 1 kilohertz. The amplitude is going to be the number of divisions that you have from your reference point to your max point. In this case, we have 2 divisions. So you get 1000 millivolts. And volt peak to peak is going to be the difference between your max and your minimum voltage. So notice that you have, in this case, 4 divisions. So 4 times 500 millivolts. And at last, your DC offset, how much is this wave being translated up and down. In this case, notice that I have the same amount of area up as I have down. So the same amount of divisions. In this case, the DC offset is going to be 0 because my reference point is in the middle of my wave. Example number 2. I recommend you guys to pause the video and try it by yourself. And I'm going to provide the answer for example number 2. Type of wave that we have, it's a sine. The period here, so I pick one point. I trace my signal until it repeats, which is over here. I only have 1 division, so I get 1 millisecond. The frequency is the opposite of, or the inverse of my period. The amplitude is going to be the distance between that reference point to your max. So in this case, I have 1, 2, 3, 4, 5 divisions. So 5 times 200 millivolts. Volt peak to peak is going to be all this distance from your min to your max, 2 volts. And once again, DC offset, the same amount of divisions here that I have over here, or the reference point is in the middle of your graph, DC offset is 0. Right? Example number 3. Type of wave, it's a sine wave. Period, I can go from here to here. So I get 1 division. So I get the 1 millisecond. Frequency is the inverse, nothing new. Amplitude now. So the common mistake is to go from the reference point to your max. So avoid to do this. So this is not going to be your amplitude, this is going to be your volt peak to peak in this case, because you're going from your minimum to your maximum value. So you already know that you have 1, 2, 3, 4 divisions times 500 millivolts is going to give you your volt peak to peak. So your amplitude can be half of that. Or another way of calculating that with your graph can be by finding the midpoint of your wave, which is over here. This is your max, and this difference is 2 divisions, so 2 times 500 millivolts give you a volt. The double of that gives you your volt peak to peak. And now the DC offset. We do have a DC offset because the wave is not the reference point, the ground. Apologize here. The ground here is not in the mid of your wave. So how do I find the DC offset? The DC offset is going to be the difference between the mid part of your wave to your reference point. In this case we have 2 divisions, so your offset is going to be also a positive offset of 1 volt because your wave is going up. Let's move on to another example. Similar one, so your wave is going up, so you're already expecting a positive offset. So pause the video and then check your answers. I'm going fast here. You guys can check the answers at the end. So I'll go over the offset here one more time. So the mid part of my wave is around here, and I go the distance to the reference point, just 1 division, so I get 100 millivolts positive because the wave is shifting up. This case you have a triangle wave, same thing applies here. Positive offset. Now let's go over square waves. This is a real picture from an oscilloscope. Notice now that my reference ground is over here, so my wave is going down. So I'm expecting a negative DC offset, so you do exactly the same thing that you have been doing, but now you have a negative DC offset. Type of wave, it's a square wave. The period of the wave, 600 microseconds, so I have roughly 3 divisions from one point to another, so I can go from this point up to when it repeats, which is here. So I get 1, 2, 3, roughly 3 divisions. The frequency is the inverse of that. Then I have amplitude, volt peak to peak. Let me just erase these so we can see the rest. Then we have volt peak to peak. And now the DC offset from the mid of your wave to your reference point, 1 division, it's going to be negative. So it's going to be negative 500 millivolts. At last, we saw all these parameters. We just need to go and cover this duty cycle. Couple of examples. It only applies for square waves. So the duty cycle is a ratio. It's the difference, or it's a ratio or a relationship between the period of your signal and the time that that signal is on. So notice on the first example here on the 50% duty cycle, the period goes from here to here, from this point to this point over here, and the time that is on is only here, and in this case it's half of the time is on and half of the time is off, so it's a 50% duty cycle. The second example, you notice that you have more time on, so the duty cycle is bigger, and here you have less time on, so the duty cycle is less. So let's go over an example. Type of wave, square wave. period, we can go from here until it repeats, which is here, roughly 2 units, so 2 times 200 microseconds. Frequency is the inverse. Now what is the duty cycle? So I already know the equation for the duty cycle. I know it's the time that it's on over my period. So I already know my period, which is 400 microseconds. Now I just need to find the time that I'm on, which is this time over here, which is roughly 1.5 divisions. If I multiply that, 1.5 times 200 microseconds, I get 300 microseconds. 3/4 gives you 75% of a duty cycle. The next example, duty cycle is a little bit shorter. Pause the video, give it a try before you check the solutions. The period, 400 microseconds, same thing from here to here, roughly 2 units. The inverse of that, the duty cycle, for easy math, I'll probably say it's half of a division, 100 microseconds, so I get 25% of duty cycle.